Hello everyone, we are from Group 7. We will present about analysis of the Millennium Bridge oscillation, the second order, the application of second order differential equation. Before that, let's introduce our team. First is, my name is Najwa Rahima with Resty number ID is 137, and my partner.
And my name is Anastasia LKA and my three last digit is 094. And my partner?
And my name is Resty Kartika Sari, and my three last digits are 066. Okay, next let's see the next video. What's next?
Exactly what happened to the Millennium Bridge. On its opening day on the 10th of June 2000,
Okay, next please. So the London Millennium Bridge opened in 2000, but began to sway unexpectedly when large crowds walked across it. Pedestrians unintentionally matched their steps to the bridge motion, creating a lateral force that amplified its oscillation, a phenomenon called synchronous lateral excitation. Engineers modeled this behavior using a second-order differential equation and found that the system became unstable when too many pedestrians were present. The bridge was closed after 2 days and later retrofitted with additional dampers before reopening safely in 2002. Next, please. And here we have the problem related to the bridge. So when the first opened, the Millennium Bridge in London wobbled from side to side as people crossed. The footfalls created side-to-side movements enhanced by pedestrians adjusting their steps to compensate. With more than a critical number of pedestrians, around 160, the bridge began to wobble violently. Without any pedestrians, the displacement of a representative point on the bridge away from its normal positions satisfy my double prime plus ky prime plus lambda y equals 0, where the approximate parameters are m equals 4 times 10 power 5 kilogram and k equals 5 times 10 power 4 kilogram and lambda is approximately 10 power 7 kilogram over second square. Show that the level of damping here is only around 9% of the critical level. And next. If there are n pedestrians, the displacement of the bridge satisfies those equations. And the effective forcing from each pedestrian is found by experiments which involve varying numbers of people walking across the bridge to be proportional to y prime, with f is approximately 200 y prime. And we have to find the critical number n0 of pedestrians such that there are more than n0 pedestrians, the bridge is no longer damped, and show that if there are 200 pedestrians, then there will be oscillation with a frequency of approximately 0.8 Hz, that is oscillation per second, and the amplitudes of oscillation of which growths are exponential t over 80. The problem was corrected by adding additional damping, a large part of which was essentially a collection of test spots, in order to bring the damping up to 20% of the critical level. What would this do to the value of K, and how many people can now walk across the bridge without counteracting all the damping? So before we solve the problem, we have to make the model definition, that is the model with no pedestrians and the model with pedestrian. So here we are going to talk about the model with no pedestrians first. So the displacement y of a representative point on the bridge from its equilibrium position, yt, without pedestrian is modeled by the standard free damped oscillation ODE. With this equation, here M represents effective mass with this value, and then K represents intrinsic damping coefficient with this value, and lambda represents stiffness coefficient with this value, and Y represents displacement or position. And next, this is the model with pedestrian. So the effective forcing F from each pedestrian is found to be proportional to the bridge velocity, that is Y prime. So F approximately 300 Y prime. If there are n pedestrian, the total external force is F total. So F total equals 3000 and Y prime. So the governing ODE becomes like that. And rearranging this into the standard homogeneous form, we got this form. And the effective damping coefficient is defined as Kf equals K minus 300n. And for the first problem, will delivered by my partner. Next, please.
Okay, the problem 1. So that the level of damping here is only 1% of critical level. Please. First, we need to calculation of damping, critical damping, or K critical. For second order homogeneous ODE, M double Y double prime plus K effective plus lambda Y is equal to 0. The critical damping coefficient K critical is defined as a value of K effective that makes that characteristic equation have a single repeated railroad, thus eliminating oscillation. For K critical is equal to 2 square root M lambda. And then we substitute by the given parameter, K critical is equal to 2 square root 4 times 10 power 5 times 10 power 7. And we calculate again. The critical is equal to 2 square root 4 times 10 power of 12. And we have the K critical is equal to 4 times 10 power of 6. This, the critical damping of K critical is equal to K times 10 power 6 kilogram per second. Next, please. And the second, we need to calculate of damping percentage. The intrinsic damping of which is K equal to 5 times 10 power 4 kilogram per second. And we compare to the critical damping, then the damping percentage is equal to K over K critical times 10%. And we substitute the K is equal to 5 times 10 power 4 and the K critical is 4 times 10 power 6. We calculate damping percentage is equal to 0.0125 times 100%, and then the damping percentage is equal to 1.25%. So the conclusion, the intrinsic damping of bridge is 1.25% of critical damping level, which is approximately the 1% level stated in the problem. Then the bridge is highly underdamped. Next, we'll present with my partner.
Okay, so problem number 2 is find the critical number of N0 of pedestrians such that if there are more than N0 pedestrians, the bridge is no longer damped. Show that if there are N equal to 100 pedestrians, then there will be oscillation with a frequency of approximately 0.8 Hertz or oscillation per second, the amplitude of oscillation of which grows as exponential t over at. Okay, so the first is we must define the critical number N0. The bridge is no longer damped when the effective damping coefficient or KEFF or K effective drops to 0. If K effective less than 0, the system experiences negative damping and the amplitude grows or instability. We said K effective is equal 0. So K minus 300 and 0 is equal 0. 300 and 0 is equal K, and N0 we got n0 equal k over 300. So we must substitute the value of k. n0 equal 5 times 10 power 4 kilograms per second over 300 kilogram per second over percent. n0 is equal 50,000 over 300. Then we get 500 over 3. We get n0 is approximately with 166.67. Since the number of pedestrians must be an integer, the first number that causes instability or k effective less than 0 is n equal 167. Thus, the critical number is n0 equal 167%. Second, we must analyze with n equal 200 pedestrians. With n equal 200, the effective damping coefficient or k effective must be negative. K effective equal k minus 300 n. K effective equal 5 times 10 power 4 minus 300 times 200. K effective equal 50,000 minus 60,000. And then we get K effective equal minus 10,000 kilogram over second. And the ordinary is m y double prime plus K effective y prime plus lambda y equals 0. And then we must input the value 4 times 10 power 5 y double prime plus minus 10 power 4 y prime plus 7 power 7 y equals 0. And we must divide by 10 power 4 for simplification. And the final we get 40 y double prime minus y prime plus 1000 y equals 0. And then the characteristic equation is 40 r squared minus r plus 1000 equals 0. Use the quadratic formula to find the roots r. We use r equal minus b plus minus the square root of b squared minus 4ac over 2a. And r equal 1 plus minus the square root of minus 1 squared minus 4 times 40 times 1000 over 2 times 40. R equal 1 plus minus square root of 1 minus 160,000 over 80. And R equal 1 plus minus square root of minus 159,999 over 80. Since the discriminant is negative, which is the square root of minus 159,999, that approximately with the square root of minus 160,000 is equal the square root of 60 times 10 power 4e is equal 400e. And we get the final of the roots is r approximately with 1 plus minus 400e over 80. The roots are complex conjugates, which is r equal alpha plus minus e omega d. The alpha is equal 1 over 80 and the omega d is equal 400 over 80 is equal 5 rad over second. Amplitude growth, which is the real part alpha, dictates the amplitude growth envelope is exponential alpha t. Amplitude growth is equal exponential t over 80. And then oscillation frequency of or f, the frequency in hertz is f equal omega d over 2p and equal 5 over 2p hertz. And f is approximately with 0.7958 hertz or approximately with 0.8 hertz. And the conclusion of this problem is with n equal 200 pedestrians, the negative damping causes oscillation at approximately 0.8 hertz with an amplitude that grows exponentially as e t over 80, confirming the instability. And the next problem will be presented by my partner.
Okay, the third problem is that the problem was corrected by adding additional damping. A large part of which was essentially a collection of despots, and in order to bring the damping up to 20% of the critical level, what would this do to the value of K, and how many people can now walk across the bridge without counteracting all the damping? Next, please. So the first, we must calculate the new damping coefficient, or K nu. So the target total damping K nu is 20% of the K crit. So K nu is equal to 20% times K crit. And we got K nu is equal 8 times 10 power 5 kilogram over second or per second. So the original intrinsic damping K is effectively replaced by nu, much higher damping coefficient. K nu is equal to 8 times x times 10 power 5 kilogram per second. So the additional damping required was 750,000 kilogram per second. And next, we must calculate the maximum number of pedestrians, or NMAX. So the maximum number of people bridge can now accommodate occurs when the effective damping based on K nu is 0. So here Kf equals K nu minus 300 NMAX equals 0, and we got NMAX equal K nu over 300. And we have to substitute the new damping value to the NMAX. So from the previous calculation, we got K nu and we just substituted it, and we got NMAX equal to 1666.67. So by increasing the total damping to 20% of the critical level, the bridge can now safely accommodate up to 2,666 people without initiating the destabilizing feedback loop. And next, so here's the visualization of the Millennium Bridge London before 2020. So here the blue dotted line represents initial condition. Let's take n equal 10, and we have Kf equal 47.0 K kilogram per second. This is highly under damped. And for the red line, it represents instability. For n equals 200, we got Kf equals minus 10 K kilogram over second. This is negative damping. And then for the green line, it represents fixed. That is for n equals 200, we get K nu equal 2% from the K crit. That is Kf equals 740 kilogram per second. And maybe we can go to the link visualization. So here, to get this graph, we use Google Colab, and we just substitute our problem here, and we get the representation of our problem. The same like as the PowerPoint. Okay, we go to the PowerPoint, please. And next, for the conclusion, will be delivered by my friend. Okay, please turn on your mic.
Okay, so the conclusion of this problem is the Millennium Bridge problem is a real-world case where very small damping, or only 1.25% of the susceptible to a destabilizing feedback mechanism, or the pedestrian force, which is perfectly modeled as negative damping in a second-order ordinary differential equation. The engineering solution, which involved the addition of 750,000 kilogram over second of damping via despots, drastically increased the critical vulnerability limit of the bridge from 167 people to 2,660. 66 people, proving the power of ordinary as a primary tool in engineering stability analysis.
Okay, that's all from our presentation from Book 7. Thank you very much, and hopefully you can understand well. Wassalamualaikum warahmatullahi wabarakatuh.